Hi y'all, welcome back. So in the last video we has arrived at this partial differential equation with the velocity profile as a function of x. Okay, speaking of that, you have to notice something interesting because I'm gonna do some conversion. Okay, so let me make a note. So note that v is only a function of x, a function of x. What does it mean? It means that the partial derivative, okay, will become an ordinary derivative. Okay, let me write it like this. Will become ordinary derivative. So, because you don't have to worry about others variable. Okay, so what does it mean? It means that you see our partial v squared over partial x squared. Now it's just gonna become d v squared over dx squared equal rho chi over mu. Okay, so this is very important terms. Okay, so this is we can do some integration here. If you remember, the second derivative is just the derivative of the first derivative. Okay, so I will rewrite like this. So d over dx of dv dx equal to rho chi times mu. Okay, so I will times dx both sides. Okay, so we have d of dv over dx equal to rho chi over mu times dx. Okay, so let's go ahead and integrate those. So you remember you have something like this, right? You have like dy equal to 6 dx, right? And then so you integrate both sides and you get y equals 6x plus c. Okay, in your differential equation or your calculus 2 class, don't forget your calculus 2 knowledge. But if you forget, this is a reminder. So using the same principle, we can arrive at, so this is dv over dx, right? Because this is integral of dy, just like this. So you get y, so now you get whatever is the d, so it's dv over dx. And here you get rho chi over mu times x plus c1. Okay, don't forget your constant when you integrate. Okay, and now let times dx both sides again. So you have dv equal to rho chi over mu times x dx plus c1 times dx. Okay, and I will again integrate it. So integral of dv equal to rho chi over mu times integral of x dx plus c1 times integral of dx, right? So you get what? You get v as the velocity profile, or v as a function of x, equal to rho chi over mu times x squared over 2 plus c1 times x plus c2. Okay, so this is your velocity profile for x. Okay, but you might ask me, Justin, why is c1 c2, right? Is it still a mystery constant, or is there a way we can find it? Yes, there is a way we can find it. It's called a boundary condition. Okay, so I'll make a note. So right now we need to plug in the boundary condition to solve for c1 and c2. Okay, so what is our first boundary condition? Let me write it in green, or actually in red. Okay, so first boundary condition Okay. So if you look at the graph, they say at x equals 0, v equal v0, right? So what does it mean? It means that, so we substitute in x equals 0 to have v. So rho times chi over mu times 0 square over 2 plus C1 times 0 times plus C2 equal V0, right? So what does it mean? It means that C2 equal to V0. Wonderful, guys. We have obtained C2. How about C1? Okay, so we need another boundary condition. So let me write second boundary condition. Okay, so what's the second boundary condition? It say at this free surface, or in terms of mathematics, at x equal h, there is no shear stress. There is no shear stress. So what does it mean? It means that shear stress tau, shear stress is denoted as tau, okay? Tau xy. The reason why it's xy is we only care about the xy plane. We don't care about xz or yz because z is irrelevant. Remember, span y, span to infinity. We don't care about that. At x equal h, okay, equal to 0. Okay, I make some notes here. If you interest in y, the geometry like y is xy. So for y, it is xy. Please take a look at figure 5.14, page 274, or if you use electronic devices, should be page 293 out of 807. Okay, what is tau xy of h? Okay, so if you use table 5.7, equation 5.60, page 277, or you use electronic device 296, you get an equation for shear stress. Okay, so what it say? It say mu times partial u over partial y plus partial v over partial x. Okay, that is your tau xy. All this at x equal h equal 0. Okay, of course, can we simplify this term? Yes, we can, because remember I'll use 0. Previously we had demonstrated, so it become mu times partial v over partial x at x equal h equal 0, right? Okay, wonderful. What is this term right here? Now we start plugging it. Do we have partial v over partial x? Yes, we do. Let me show you guys. Here. Right, remember partial v over partial x is dv over dx because it's the same, but partial derivative and the ordinary derivative is the same because v is only a function of x. Okay, so we plug it in. So we say mu times rho times what? Mu times rho times g over mu times x, right? Plus C1. Do we have C1? No, we don't. That's why we're solving for it. C1 at x equal h. Okay, I will highlight it so y'all know that what, like I'm substituting. Okay, equal 0. Okay, so why is the yellow term in at x equal h? I'm just gonna go ahead and again substitute in h. So it's rho times chi over mu times h plus C1 equals 0. You cancel out the density term on both sides, rho. So you get rho times chi times h over mu plus C1 equals 0. And then from now, you can solve for C1. So your C1 is negative rho times G times H over mu. Excellent. So now we have our C1. Okay. So what we're gonna do next, we're gonna stop this video because it's 10 minutes, and I will see you in the next one. Thank you.